there's going to be a lot of analogs between magnetostatics and electrostatics because you have one curl equation and one divergence equation. But there are differences because a non-zero part on the right-hand side appears with the curl equation and not with the divergence equation. Another way to say that is that it's the current that produces magnetic fields in magnetostatics, and it's the electric charges that produce electric fields in electrostatics. Okay, so what is inductance? We talked about it in a kind of an abstract way, independent of any coordinate system. If you have two loops, say C1 and C2, and each loop is described by a contour, C1 and C2, and inside of that contour is some surface, S1 and S2, and suppose you got a current flowing in one of the loops, then that current will produce a magnetic field, and that magnetic field will go through surface S2 of contour. And that's a way to describe a kind of neutral inductance. So the magnetic flux from loop 1 to loop 2 is a magnetic field from loop 1 integrated over the surface S2. And if you normalize out the current, you get what we call the mutual inductance. And that's in units of, mutual inductance is in units of Henrys. Magnetic flux is in units of Weber. And a Weber is a Henry ampere. Okay, if S2 happens to have more than one loop associated with it, if it's a coil of wire, then the mutual inductance is just multiplied by the number of loops, N, and we have this term flux linkage, which is the number of turns times the flux, magnetic flux. And then you can think about the magnetic field from B1 flowing through its own surface, and then you get the idea of self-inductance. So the magnetic flux through its own surface. And since we're just dealing about loop 1, you can drop all the subscripts since you have the magnetic flux as the integral of B dot ds over the surface. So magnetic field fluxing through its own surface gives this idea of self-inductance, or just what we'd be calling inductance. So flux per inductance. Okay, so how do we apply this for something like a coaxial cable? We're asked here to find the AC inductance per unit length. And if you have a coaxial cable, here's the cross section, you've got an inner conductor and you've got an outer conductor. The radius of the inner conductor is A, and the radius of the outer conductor is B. And if you're operating in DC, for DC currents, then that current flows entirely inside of that inner conductor. We'll talk about that a little bit more today. However, when you use a coaxial cable, you're interested in the AC inductance per unit length. So as the frequency goes up to, say, the frequency range where you would want to use a coaxial cable for signal propagation, that might be in the gigahertz range. So AC frequency is 1E9 hertz, 1 gigahertz. Then what happens is the current tends to flow only on the surface of the conductor. There's the electromagnetic skin effect where current flows on the surface of metals. So the current I, then, you can imagine, is residing on the surface of that inner conductor. And to find the inductance per unit length of this coaxial cable, we will use this right figure and apply these two equations. So the inductance is the magnetic flux normalized by the current, where the flux is the integral over a surface of B dot ds. Okay, so the first step is to find the magnetic field inside of your coaxial cable. So the magnetic field is going to reside between the two metals, shown here in orange. And by the right-hand rule, right, you put your thumb in the direction of the current, and your fingers will be in the direction of the magnetic field. So we've got a direction of the magnetic field, and because of the symmetry, we can use Ampere's law to solve for the magnetic field. Okay, so just a reminder of Ampere's law. If you want to find a magnetic field using Ampere's law, you start with the curl of H equal to J, Maxwell equation. Take the integral of both sides over a surface and then apply Stokes' theorem. And that gives you the integral of the contour C of H dot dl is equal to the current enclosed. Okay, so to apply Ampere's law to find the magnetic field, we choose an Amperian contour, okay, which is that contour here. And we don't know what the magnetic field is along that contour, but we do know that it's constant by the symmetry of the problem. You would expect that if this is an infinitely long coaxial cable, then the magnetic field would just have a variation in the radial direction away from the center core axis, or in this case the z-axis. So we don't know what the magnetic field is inside the coaxial cable, but we know that it's constant. We argue it's constant over that contour. That allows us to do something very similar to Gauss's law in electrostatics. We apply Ampere's law, in this case cylindrical coordinates. So the integral is going to be a contour over the arcuate, radius dp. And then we're just going to put a symbol for h. It's in the phi direction in cylindrical coordinates, and we'll give it a symbol hv. We don't know hv, but we can pull it out in the integral. dl in cylindrical coordinates around this contour is phi hat r dp. And then the current enclosed inside of this contour is just the current I. Okay, so that's your contour, and then the current I is what's enclosed inside of that contour, and that's what appears on the right-hand side. So phi dotted with phi is 1. hv comes out of the integral, and you're just left with d phi in the integral, because for any contour, that radius is going to be constant about that contour. You have hv times r times the integral from 0 to 2 pi of dp is equal to I, and that lets you solve for the magnetic field. Okay.
If we're calling the radius of the circle HR, would, for that equation, the little r equal the radius of the big circle minus A?
One more time on I missed the first part of your question.
Well, would the little r be the radius of H minus A?
This one here.
Yeah.
This R there.
Yeah.
Yeah, so this is the, so you're asking is, should this R here be referenced to A? Right? Is that your question? Because the
Yeah.
current is on A.
Yeah.
Yeah.
So it would be the distance from A to wherever the...
Yeah. That's a good question, and we'll take a closer look at Ampere's law today to see some variations of this geometry. But the idea here is it's just R, okay? And that's because this quantity here this quantity here is the differential length in cylindrical coordinates. Differential length. Okay. So phi hat is the unit vector around that contour, and then a differential length on that contour is distance from the z-axis times the differential angle, and that gives you that little bit of arc length. So r is measured, is the cylindrical coordinate r from the z-axis. And what's interesting about Ampere's law is it's only the charge that's enclosed inside of your Amperian contour. It doesn't depend on whether or not you've got a solid metal or an infinitely thin wire. What only matters is the current that is inside of that contour. Okay, so I'll do an example later to illustrate that point. Okay, so once you have the magnetic field, we can finish this problem. So the H field is phi hat H phi, and that is equal to phi hat I divided by 2 pi r. You can see our magnetic field depends on I. So if you have a stronger current, then you have a stronger magnetic field in your coaxial cable. And as expected, there is a relationship of the magnetic field strength that depends on the distance away from the z-axis, 1 over r. Okay, so what is the B field then? So, we can start there, okay? For an air-filled coax, mu is equal to mu naught. Or in any case when your coaxial cable is not filled with some kind of magnetic material, or relative permeability is different than 1. So mu is equal to mu r, mu naught. Just equal to mu naught, for example. Your coax is filled with air. Well, actually, most dielectric materials have a relative permittivity of just 1. So this is often the case. Okay, so then B, magnetic field B is equal to mu H, or mu naught H. Okay, and then for the magnetic flux, so once you have the magnetic field, we're halfway there, because given the magnetic field, we can now compute this flux. Okay, and this is where that other loop comes in to play. We talked about there's 2 loops in this problem. One is the contour for the magnetic field, and then the other one is this red line, which represents the surface of our infinitely long coax. So you have to kind of imagine the current I is coming out in this direction, out of the page. It's going out to infinity, and then it's coming across that infinity and coming back on the outer conductor. Okay. And so the surface for our fluxing is represented, the cross-section is here, this red line, but that is representing the whole surface along the infinitely long coaxial cable. Okay, so let's see how that works out mathematically. We have B, so we can now compute this magnetic flux. So, given the magnetic flux then, or given the magnetic field, phi is equal to the integral over the surface S of B dot ds. So that's going to be double integral, and then B is phi hat mu naught I divided by 2 pi times r, and then the differential surface now is going to be, so here's your magnetic field, and it's fluxing into that surface represented by the red line. Okay, so the direction of the differential surface element, which is infinite number of little squares on that red line, is also going to be in the phi hat direction. And then the length of your square is going to be dz dr in cylindrical coordinates. The differential surface element is phi hat dz dr. And then the v Z limits of integration go from 0 to the length of your cable. And then R goes from little a to B. Okay, so that is the magnetic flux for the coaxial cable, and I think that's probably the trickiest part, is to see that there is in fact a surface there for this infinitely long coaxial cable, and that red line is showing the cross-section of that surface. Okay, so we can crank out this integral. Phi dot phi is 1, mu naught I over 2 pi comes out of the integral. Integral of dz from 0 to L is just L. So you're left with the integral of 1 over R dr from A to B. I divided by 2 pi comes out. The length, and the integral from A to B of 1 over R times dr. Okay, somebody remind me, what is the integral of 1 over R dr? Okay, natural log, so it is natural log of B over A. Mu naught I L over 2 pi natural log of B divided by A. So the inductance then is the magnetic flux divided by the current I. And you can see that the current I cancels out. You get mu naught length over 2 pi times the natural log of B divided by A. The inductance is a characteristic parameter of your materials and geometry again, and it should not depend on the current that's flowing. Just like capacitance, it just depends on the geometry, geometrical parameters, L, B, and A. And it only depends on the material parameter. Okay, now for our infinitely long capacitor, what's maybe a little more interesting is not the overall capacitance, although if it's smaller, it would be interesting. What's more useful for us, and if we go back to chapter 2, we looked at the inductance per unit length. So that is going to be L prime. So that's the total inductance normalized by the length of your coax. So the inductance per unit length is mu naught divided by 2 pi times the natural log of B over A. And at this point, this would be somewhat intellectually satisfying because we took this equation for granted in chapter 2, but here we are deriving it from first principles. Okay, so this is the AC, or high frequency inductance, per unit length of the coaxial cable. All right, any questions on that? The nice problem of a solenoid on the homework. We will do another inductance problem. Take a look at that, due on Friday. All right, so we introduced or reintroduced Ampere's law, right, to solve this problem. And you've all seen Ampere's law in your physics courses. And that was kind of this part here. Right. To get to Ampere's law, we'll start with Maxwell's equations, take the integral over a surface on both sides and apply Stokes' theorem. And Ampere's law is here. Integral over the contour C of H dot dl is equal to I. Let's take a look at two examples of Ampere's law that are a little bit different than this case here. There there was a question on it earlier, so let's take a look at kind of two sort of limiting examples. Illustrate Ampere's law a little more. Okay, so the first one, let's do an infinitely long wire. Okay, so instead of an infinitely long coax, I want to just look at a wire. Okay, what do I mean by that? This thing is, so if you got an x, y, z coordinate system, I want to imagine I'm looking at a wire that is just infinitely long along the z-axis. Okay. So it goes up and down your z-axis infinitely. So it's really long. In a practical sense, we just mean that the wire is really long. Coat hanger from that side of the room to that side of the room. Really long, right? Okay, and let's say there is a current flowing in the wire in that direction. The current has direction. And we want to ask, well, what is the magnetic field from this infinitely long wire? All right, so we have cylindrical symmetry again because this thing is infinitely long. So for us, find the magnetic field or magnetic flux density vector. H, B is mu H. H is the magnetic intensity or magnetic field. So find B using Ampere's law, or so far, this is the only way we know how to find B. The other way is B of Savart. That was talked about a little bit last time. You probably saw that also in your physics courses. So let me remind you how to find B using Ampere's law for this particular case. All right. So Ampere's law is a given rho over the closed contour C of H dot dl. And I'm gonna, for the moment, write this explicitly to the side. So we write Ampere's law like this, right? But remember, the right-hand side I is equal to that. So the only thing that's important with respect to the current is how much current is inside of that contour, right? How much current is flowing through the surface through that contour. Remember that when you're thinking about Ampere's law. Okay, so we want to pick an Amperian contour C such that even though we don't know the magnetic field, since that's what we're looking for, we can argue that it is constant over that contour, and that allows us to pull this magnetic field H out of this interval. So somebody, what would be a good choice for an Amperian contour for this problem? That's the correct idea, but we're thinking about a contour now. Circle. Okay. So, good choice for an Amperian contour is a circle. All right. So that circle then we can proceed then with Ampere's law, with our Amperian contour. Now, contours and surfaces have directions, right? So this blue contour here, I can go around the contour in one direction, or I can go around the contour in the other direction. And the surface bounding that contour, I can think of the surface up or the surface down if I want to pick a direction for the normal. So you tie because of Stokes' theorem, the direction of the contour is tied to the direction of ds for your surface. So here, you've got a contour C, and on the right-hand side you've got a surface S, so you've got ds. So you can remember this by the right-hand rule. Your thumb is in the direction of the current. The proper contour direction is going to be in the direction of your fingers. So for this problem, contour C is the opposite. Okay. So, integral. Contour integral is a line integral. The magnetic field, now we don't know what it is, but we can put a symbol for it. It's in cylindrical coordinates, it's in the phi hat direction. And the symbol we use is hv. And then the differential length around that contour is phi hat r dphi. Okay, so that's the differential length in cylindrical coordinates. And so that is in the phi hat direction, and the arc length is r dphi. And then the current enclosed inside of that contour is your current I. And we integrate from 0 to 2 pi. Okay. So phi dot phi is 1. HV can come out. R can come out, because it's constant over that contour. You got an integral from 0 to 2 pi of d phi, that's just 2 pi. On the right-hand side is the current I. Okay. So h phi then is I divided by 2 pi times R. So the magnetic field H is phi hat I divided by 2 pi times R. What's interesting about that, well, that's the same thing as the magnetic field from a coaxial cable. Magnetic field is phi I over 2 pi r. Same thing here, magnetic field is phi I over 2 pi r. And that's because it's the current that's enclosed that's important in Ampere's law. In both cases of the coaxial cable and the infinitely long wire, the current enclosed is our current I. And the coaxial cable also has cylindrical symmetry because it's a solid rod along the z-axis. Okay, so whether or not you've got the current flowing on the surface of this interconductor or the current just flowing inside of this wire, the resulting magnetic field is the same. Kind of, right? I mean, in the coaxial cable, even though the equation is the same, you don't have any current for R less than A. You have no magnetic field in there either. All right. Any questions on that? Let's do another, sort of the opposite extreme case. Let's do another infinitely long problem. Now, I'm going to give the wire some diameter. Twice the radius, or 2 times A. And I want to talk about this DC current a little bit. Okay, so DC current, and infinitely along the wire, the diameter. Sometimes you do, in fact, still connect wires to wires. And then we're talking about a DC current. Okay, so nothing AC. Well, what does that look like? Let's draw a cross section. Okay. So let's call this the x-axis and that the y-axis. And now I've got a wire with radius A, so all of my current is flowing in DC. All the current is flowing uniformly inside of this interconnector in DC. All right. Think of all solid block of metal with R less than A. Okay. We can describe this current. So current I flows in the plus C direction. Okay. And if the current I is flowing uniformly, okay, what is the current density through that wire? You're told that this is a DC current, it is flowing uniformly through this wire of radius A, diameter 2A, and given all that then, how would you describe mathematically the current density?
I over pi squared.
I over pi squared, right. And then it has a direction, because J is a vector.
Yeah.
So J then is going to be V hat I divided by pi A squared, current density. So I like this problem because it really emphasizes the meaning of current density. Right? The total current I flowing through the area pi A squared in the case when it's a uniform current flowing through the area. Okay, so units then are in amperes per meter squared, as just as it should be. Okay, so now in DC, if this were AC, right? If this were now a very high frequency current, then that current would flow to just the surface, and then you would get magnetic field only outside of the wire, just like a coaxial cable. But in DC, you do get magnetic field inside of that wire. So let's see how we might solve for that. So question then is, find the magnetic field for all distances away from our z-axis. All right, so we can argue that if this is an infinitely long wire again, then the magnetic field will only have z or r dependence. The strength of the magnetic field should only depend on the distance away from the z-axis. So we can apply Ampere's law symmetry. Apply Ampere's law. Integral over the contour C of H dot dl is equal to the currents. Okay. All right, and then the current here is I, but let me write it explicitly in terms of the current density. Since we've got current everywhere inside of our wire, we're going to need this more general form. Our Amperian contour, good choice of the Amperian contour, is going to be another loop C. And that, the radius of that loop is R. R is the radius of that contour. Okay, so we can now solve using Ampere's law. So integral over that contour. We don't know h, but let's give it a symbol again. We have hd. dl is v hat r dv again. This Amperian contour, integrated from 0 to 2 pi. Okay, now that is the right-hand side, which is the current I. So the tricky thing here is that even though the magnetic field is only depending on R, as you change the radius of our contour, right, as the radius of the contour is changing, then the amount of current inside of that contour is also changing. The right-hand side depends on the radius of our contour. So how do we handle that? Okay, so another way to say that is, as my Amperian contour, if I look at the magnetic field at different radii, then the current is not constant like those other problems. If inside R less than A, then the current is changing depending on R. Okay, so the current then, we need to solve for the current enclosed using our current density. We know the current density, double integral for surface. Current density we already found is z hat I over pi a squared. And then the differential surface through our wire in cylindrical coordinates is in the z hat direction. And then the two edges of your square are r d phi, that arc length, and then dr. Differential surface element in the z hat direction in cylindrical coordinates. And then we integrate. What are going to be our limits of integration here? for this particular problem. So if you look at the right-hand side, what we're trying to do is capture the current that is inside of our M-period contour. So in order for us to properly capture the current inside of our M-period contour, it's done here with the limits of integration. So somebody, first, limits of integration on phi, and then the limits of integration on r. Yeah.
Should you have r squared, like I over pi r squared? Because it's not changing too. Is the current changing? Current density?
The current density is not changing. Yeah, the current density is a constant. So current density,
So on the surface part is changing.
yeah, because current density is, since the current is uniform over that cross-section, right? Then the current density is constant for anywhere you are inside of that wire. So you take the total current I and you divide by the total area, which is pi a squared. So it's I over pi a squared. The current density is not a function of position inside of your wire. And that's because the current is flowing uniformly. I over pi a squared. Good? How about just the limits on phi? What should that be? 0 to 2 pi, that's correct. That gets us around the wire. And then, how about the limits on R? 0 to A, that's the right idea, but 0 to A would capture all of the current.
0 to R, you can have a function.
Yeah, it's at 0 to R, so you can have a function. In other words, the current inside of your M-period contour is in fact a function of R. Right, so it's going to be from 0 to R. Okay, excellent. All right, so we can then crank out the math. The left-hand side is the same. Phi dot phi is 1. H phi can come out. R can come out. And then you have the integral from 0 to 2 pi of d phi. So that is H phi R 2 pi. And then the right-hand side, z dot z is 1. I is a constant, so that can come out. Pi over a squared is a constant, that can come out. And then integral on d phi is 2 pi, that can come out. We're just left with I 2 pi divided by pi a squared times the integral from 0 to r of r dr. Okay. The pi's cancel. You've got 2I over a squared. 2I over a squared, and then the antiderivative of r, so it's r squared divided by 2 from 0 to r. So you get 2I a squared times r squared over 2, which is I r squared 2I. 2's cancel with I r squared divided by A squared. I R squared divided by A squared is the current inside of your loop with the variable R. I could have almost guessed that, right? Because what we're saying, if the current is uniform, then the current inside of a loop of radius R is going to be I times the ratio of the area inside of the contour, which is pi R squared, divided by the total area, which is pi A squared. So that makes sense. So the magnetic field then, H phi, is I divided by 2I times R divided by 2 pi A squared. Okay, or the magnetic field is phi hat H phi, so it is phi hat I times R divided by 2 pi A squared. And that's true for R inside of your wire. Okay? All right. Now, what if we are outside of our wire? Okay? If we are outside our wire, then the problem looks like this. For R greater than A, still got your wire, but now your contour is going to be up there. So, what is the magnetic field for R greater than A? Phi hat I over 2 pi R. We've already calculated it 3 times, right? Because the only thing that matters is the current that's enclosed, and for any radius of a contour, as long as that radius is greater than or equal, is greater than A, then the current is not changing as that contour is changing in radius. So the only thing that matters is the total current I enclosed. And so by Ampere's law, we get I over 2 pi R again. For R greater than. So we can plot that. On an axis, so if I were to plot my magnetic field as a function of radial distance away from the wire, and I were to plot the magnetic field, then what? We got this here, where R less than A. That is a linear function, right? So the magnetic field H is increasing linearly with R. Okay? The magnetic field all the way up to A. magnetic field is IR over 2 pi A squared, okay? Increases leading with R. And then, once you get to A, the magnetic field drops as 1 over R. The magnetic field is I over 2 pi R. At R equal to A, the magnetic fields are the same, right? It's kind of nice is that the first equation at R equal to A is I over 2 pi A. And the second equation at R equal to A is I over 2 pi A. So they meet there. Another way of saying that the tangential components of H are continuous across that boundary. There's a boundary condition on magnetic field also that we'll talk about. Okay, so this is kind of an interesting problem because here you've got a magnetic field that is not dropping as R over some distance R less than A, and that's because the current is you're looking at radii inside of the wire. So inside of that wire is linearly decreasing, depending on how far away you are from the wire. Okay, any questions on Ampere's law? So I think you can take Ampere's law as the analog of Gauss's law, right? Works a lot like Gauss's law. If you can argue some symmetry, then you can solve these problems very quickly by picking the proper Ampere law. Okay, so that's all we got for today. We'll see you next time.